want to talk about representations of waves. And so I'm going to use sound as an example. So we start with this representation of air molecules right here. So if we did a snapshot of where all the air molecules are in the room, then we have right here. They're not perfectly evenly spaced, but there's some random distribution. There's some places where it's clumped slightly more than other places, but overall it's pretty evenly distributed. I have air molecules pretty much everywhere. Now, all these air molecules are moving, so if I did a snapshot slightly more, then it would look different, but this represents sort of an average moment in time. Now, as we're talking about making sound, for example, we're talking about making sound. Basically, we have vocal cords that are vibrating back and forth. And so let's represent a vocal cord. And notice that in one case, it's pushing air. In the other case, it's sort of sucking air. So if I have a vocal cord like this, and as it pushes like that, it's basically going to take these air molecules and it's going to push them out of the way. Now, if this thing comes back, it's already pushed those air molecules out of the way, and so it creates this sort of like a vacuum right here, where you've got these areas where you've got that high pressure from the initial push, and then you've got these areas where there's just not as much. And so what you end up with is something like this, where you've got these places where there's a lot of molecules and places where there's not many. This is known as compression. And this right here, where there's not as many molecules as we had before, again, given our average where it's evenly distributed, we now have an area where there's a lot fewer. This is known as rarefaction. It looks like the word rare with a faction underneath it. So rarefaction I have to say it quickly, rarefaction. So that's rarefaction right there, these areas right here. So we have compression, rarefaction, compression, rarefaction. And as it's hitting your eardrum, the compression hits your eardrum and it pushes it inwards towards the inside of your head. I'm assuming that the compression wave is higher, it has a higher pressure than the normal pressure inside your head. Compression wave hits, pushes it inwards, and then you followed by this rarefaction where your eardrum basically gets pulled back out. And I always vision this like a sort of a Morse code that your eardrum gets pushed in, and we represent that as, that sounds like the letter A if it happens quickly enough. It's not that exact. That was just sort of to give you some sort of an image. So we have these compression, rarefaction in some sort of combination. Now, the compression waves don't happen on a regular basis under normal speech. Now, you can hit regular basis. So I did that in another video where I was talking about beats. I can try to represent and get, well, sort of. It depends upon the morning. Oh. If I'm hitting a single pure note, then those compression waves are evenly spaced apart. But under normal speech, they're not. And actually, what I did just then, I was trying to represent that as a pure note. Human voice can't do it. That's why we all sound different. Some people can get a lot closer than others. I'm not one of those people that can get closer. So if I have these points of rarefaction, compression, well, if I had to draw waves like this every time, that would be a huge waste of time. I need to somehow represent rarefaction and compression a whole lot faster. And so there's basically three ways that can be represented when I'm dealing with sound. Now, the first one got my compression or rarefaction. I can also deal with that with a slinky, the same type thing, where there's at some points where the coils are closer together, some points where the coils are farther apart. However, still, it's not easy to draw a slinky. And so we can first represent this as a series of waves. Imagine like ripples in a pond. You throw a rock into the middle of a pond, and you get basically what we see as ripples. It's really, we see the crests. Now, in between the crests, there's a trough. But when we draw it out this way, we just basically draw the compression. This is sort of the peak of the compression. In between the compressions, you've got rarefaction right in here where you see nothing. So compression and rarefaction. Now, the other way to represent it is more, that's sort of an overhead view. The other way to represent it is more like a sine wave or a cosine wave, where you've got the peaks at the high compression and the trough at the low compression. If I'm dealing with a compression wave or a longitudinal wave or P wave for you geology people out there, then we have these points of compression, low, and high. Now, transverse waves, where the particles are moving perpendicular to the direction of the wave, then we basically have the same, generally represented like this, but it can also be represented like this. And for the shear waves or transverse waves, yeah, not like this. This really only works for compression waves. So that's how to represent it. In the course of, well, definitely in class when I do these things, I'm going to represent it by these different ones. But if I'm talking about sonic booms and things like that, this, or Doppler effect, this is the most convenient way to write it. If I'm talking about the superposition of waves, in other words, if I'm talking about interference, constructive and destructive interference, well, this is typically the easiest way to write it. And if I want to give some sort of physical representation, that's usually the easiest in terms of representing it. However, it's a nuisance to write. So, again, 3 different ways of expressing compression waves especially, and 2 ways especially dealing with longitudinal waves. Right there, those are the, transverse waves. Any of them can work for longitudinal, also known as compression waves. These 2 work for the transverse waves. I hope that made life better for you.